I welcome you all to the Spark Research YouTube channel. This is Dr. Vichandra, Assistant Professor in the Department of ECE. And in this session, we are going to take the contents from this course Signal Processing. And we are going to take the contents particularly from this fifth unit. And this is the second and the last session. And not only for this unit 5, but for this course also. And in this session, we are going to cover these topics: your Butterworth and Chevesy filters, design of IIR low and high pass filter using this Butterworth and using this Chevesy filter, and we'll also look into this impulse variance method, how to find out the filter using this impulse variance method. So the content may be the beneficial for your GATE exam purpose also, so you can stay tuned and we'll come with some GATE related questions as well, right? So here is the syllabus for this fifth unit, and here is the contents that we are going to take in this session. Right? So let's go ahead. So the question number first is that like how will you design the filter? So in our previous session we have discussed that how to design the analog type of the filter. So we will have a one low pass or prototype of the transformation. So which is the basic purpose, the basic version of the and any type of the filter. So what type of the basic version? So here is that is the prototype. So see here the HPS is equal to 1 over S plus 1, and this is the basic prototype, and this will be valid for all type of the filters, whatever the types of the filters you wanted to design. Only thing is that you have to replace the value of S for different type of the filter. Right, and so this is valid for the first order type of the filter only. So this is the very basic and very simple and very important one as well, right? And you can get the frequency response by substituting S is equal to j omega, and you can get this, and at the same time you can get the response, that is the amplitude, right, the magnitude. So this is the HP, the magnitude you will get. And so if you wanted to plot this HPS is equal to 1 over S plus 1, so here is this one. And suppose if you want to design the low pass filter, since this is the basic prototype which will be valid for all. So if you wanted to design the low pass filter, then what to do? Just replace the value of S is equal to 1, S by omega C. So here put the value of S by omega C, you will get the low pass filter. So this is the how can we design. If this is the, of course this is analog one. So here and also how, like, just replace the S is equal to S by omega C, and then you will get the magnitude, and this is the magnitude, right? So this is the low pass filter, that is how we'll design. Similarly, you can design the different types of the filter like high pass, and band stop filter. For details, you can go to the previous session. I am not going into that much details. Since this is a very basic and very important one, this will be used here also. That is why I am just giving the introduction about this, right? Okay, so let's go ahead. Now we will jump into the Butterworth and the KYC. So these are the digital filter design, right? So if we look into the Butterworth type of the, first of all, what is this digital filter design? So in the digital filter design, first of all, you should remember that whatever the we'll have in the S plane, we are going to map into the Z plane. That is, S plane means the analog, and Z plane means the digital filter, right? So here is the, the and also you have to wrap in these frequencies in the Z plane. So how will you wrap these the frequency to the Z plane? So we have already seen in the previous session, and here like it just the all the values of the the S plane, it will wrap into the Z plane in the inside the unit, right? And that is in the left side, and the right side it will outside to the unit circuit, right? And if you look into the difference in between the Butterworth and the Chebyshev filter, so Butterworth will have the sharp response, right? So there is no ripple at all, and this one have the rippleness. So this will be the Chebyshev filter. Now you may ask that what is the difference in between this like Chebyshev filter and Butterworth. So this is the one of the difference, but advantage is that if ripple factor, that is if ripple is there, it will be easy to design. So sometimes we may not need the sharp, right? So ripple factor, if it is ripple factor is 1, then it will be your, that is ripple factor, that is zeta is equal to 1, that it will be considered as a Butterworth. And if it is the other numbers, like apart from the less than zeta is equal to 1, then this will consider as the Chebyshev type of the filter. And is the magnitude you can check for both. So let's dive into the details of both. So here the list of the Butterworth prototype functions with 3 dB passband ripple specification. So the order one divide 1 over s plus 1. If you remember the prototype, right? The filter for prototype. Then for first order it is 1 over s plus 1. Similarly for second order 1 plus s square plus these things for third order, fourth order, fifth, and sixth. Right. Here condition is that zeta is equal to 1. So this all these belongs to the Butterworth. If zeta is different, like suppose here we are going to take if zeta is 0.3439 and zeta is 0.5, then these are belongs to the Chebyshev type of the filter, right? So here these are showing the prototype functions for type 1 and type B. Type 1 with the why we are considering zeta is equal to 0.34. So here the prototype functions with the passband ripple specifications with me 1 dB and half dB, right? Ripple specifications. So that is why we are considering. So corresponding the different prototype functions for first order prototype, this one, second order, third order, fourth, fifth, and sixth order. Similarly for half dB Chebyshev filters, your the first order. So these are the basic version of the prototype for digital filters. This are particularly these are the prototype for Butterworth and these are the prototypes for Chebyshev filter. So these are the building blocks of the digital filter design. So very important. And so analog one we have already discussed the previously, and these are for the digital, right? So now let's see the some more details about it. So following two equations must be satisfied in order to determine the prototype filter, right? So the gain here gain will be of course the 20 log and 1 plus zeta square, and so as, and also you can calculate. And zeta, how will you calculate? So zeta you can calculate 10 to the power g to the power 0.1 ap and minus 1, and n is the order. If you wanted to find out the order for any filter, then you can use this equation and find out, right? If order is closer to 1, you can use the order 1, and if it is near to 2, 3, 4, 5, whatever, it will your order Butterworth filter or the Chebyshev filter, the order will depends on the value of n. So you can check this, right? So here suppose the order is 1, this is the curve for n is equal to 1, n is equal to 2, n is equal to 3. So like it will be your curve will be like this if a higher order is there, right? And this is the magnitude, right? That is you can find out. Similarly for Chebyshev, here is the AP and the AS, and the order you can calculate for using this equation, and the zeta, that is ripple factor, you can calculate using the same equations, that is eta is equal to square root of 10 to the power 0.1 AP minus 1, right? And the cos inverse you can find out, and the response is like since it have the 1 dB or 0.5 dB ripple, so you can check that it will have the ripple, the so this is not the smooth curve. So if it is zeta is equal to 1, then only it will have a smooth. That is the case of the Butterworth, right? And this is the case of the Chebyshev. So here ripple is there, so that is why. Okay, so the important things that you have to remember, point number one, how to find out this order, that is n. This is the equation, right? So this is the one of the most important equation, that is find out the n, and then you can find out the AP, and then further you can find out the if the zeta value also, like if it is yeah, it will always be 1 for Butterworth, no need to find, and for this one you may need to find for Chebyshev, and further you can find out the h of z, right? So that is the final step. So let's see the some details, some questions. Before that, conversion from analog filter specification to low pass filter. So here you can see some details, the notations here, how to find. So omega AP is the low pass here, and omega AS. So here this is the cutoff, and so pass band frequency is, this is also called, and this is the called the stop band frequency is, right? And here omega APL, omega APH, all these details are there, so you can read here. APL is your lower cutoff frequency in the passband. APH is the upper cutoff frequency in passband. So likewise, you can check all the details, right? And for all these low pass, high pass, and band pass filters, so what will be the prototype specifications? So BP is equal to 1 for all these, and Vs is equal to omega As by omega AP, and likewise. So for the all these four, the filters, we can find out the values of the BP and Vs. So these are the another important terms. If you remember, it will be easy for design the filters. So let's take the some questions. How to design the filter? So let's design the digital low pass butterworth filter with the specification 3 dB attenuation, pass band frequency is given, and 10 dB step band attenuation at 3 kilohertz, and sampling rate is also given, right? So sampling rate, so here you can find omega dp, that is twice pi f, and so you will get omega dp and omega ds, that is sampling. You can also get the frequency and time period you will get like this. Okay, so find out the omega ap and omega as, because we are going to find out what the low pass filter. So we have to get the omega ap, that is where exactly the pass band and stop band is there, right? So then you can again these equations you can check in the previous the sessions. We have already seen how to find these equations and put the values and get the values of the omega ap and omega as. Apart from that, vs you can get the value with the ratio of omega s and omega as, and then you can find out the zeta from the same equations, and then finally find out the order. So since the n is very close to this 0.8, means the very close to 1. So how will you find this n? So just take the previous slide. The equation is there. So use the same equation in order to find out the order. So order will be 1, right? So order 1 means the what will be the prototype corresponding to this order 1. The prototype will be this one, right? So this prototype is valid only for first order. So very important one. And why are we using this? So check the the second slide, right? We have already discussed. Okay, so after getting the values, put the value of the the s, and what should we put the value? S by omega p, in order to find out the what type of filter we are designing. Low pass filter. So again same thing, so replace the value and get the value of h of z, right? So then of h of z you can find out and solve these equations, you will get the h of z. So this is nothing, this is your low pass filter, right? So this is the one of the techniques. So how to find, let me tell you. Again find out the omega ap omega as, since this is related to the low pass filter. If it is a stop, the high pass filter, the band stop, then you have to find the omega ap omega al and the various frequencies, right? And then after finding omega ap omega s, find out the vs, and then find out the zeta. Why are we finding zeta? So that we can find the ripple. Already for butterworth, like this is will be one need to find also. Then find out the order. Why do we need to find the order? So that you can identify the prototype. This is the your prototype. So this prototype is valid only for n is equal to 1. So if n is equal to 2, then what will happen? 1 over s square n plus something like, right, likewise. So just find out the prototype and then put the value of s. S will be for low pass filter. S will be how much? Omega divided by omega. Then put the value whatever you got it from here, and then solve it, you will get h of z. So these are the steps to find out, right? So here is the another similarly another question, so related to the high pass Chebyshev filter. Same technique, find out the omega d and then omega a. Also you can find out then hps. Here find out the zeta value, and depending on the order, again you can find the prototype function, and after prototype put the value of s, and then find out the h of z, right? So these are the techniques to solve. Okay, so some more questions related to the butterworth. Here you have to find omega h, omega l, omega ah, omega al, all these things. So you can check in the second slides why we need to find all these parameters. After finding all these parameters, again find out the order, that is n. After finding the n, you can find the prototype function and put the values, and then get the final value of h of z. Okay, one more questions related to butterworth, so you can check these details. And so here the some introduction, like whatever the details about the impulse variance method. So what is the impulse variance method? So here actually major difference is that instead of using the transfer functions, we are going to use the inverse Laplace transform technique. This is we are going to use one of the technique in order to solve the filter or in order to get the h of z. So how we'll find out? So h of s is there, no need to use the transfer function. Directly we'll use the inverse transfer function. So L inverse, that is inverse Laplace transfer function. So we'll get right. So h of t, like this is your L inverse of how we'll get the h of t. So you can get back into the time domain from the inverse function if h of s is given, right? And then you can the impulse response with the sampling as a scale factor, which will follow as that. And then you can actually will take the question so that we can find out like the how to find out the area. So h of s is given. So what we'll do directly, we can convert h of s to h of t using the inverse Laplace transform, and then input is there, right? So once you will get this function, after that what to do? So z transform you can find out using z of e to the power minus en as per the inputs only. And after getting this value, you can replace the value of in order to find the value of e naught. And so h of z will be the you can once you will find out the remaining parameters, you can put h of z. So this is actually the direct method to find out. So here omega is equal to 0 now. In that case you will get the h of e of j omega, so that will be equal to h of 1. And similarly you can, after finding the value of h of 1, you will get the h of z. So this is actually the inverse type of the methods to find out the your filter design technique. So you can check the some more questions. Thank you to the system.